Hi, in this video, we want to take a look at using more than one model to model a particular target variable. Typically, we don't want to be in this situation. We're in the situation where I've got target variable and I'm not quite getting the accuracy that I need off of just one model. Now, this is going to be different than an ensemble model where we have a bunch of individual models that I combine. Here, what we're going to be doing is we're going to be trying to break up our target variable so that I can model just certain aspects of it. So, for example, let's say that I have a numeric target variable that I'm having trouble modeling. And what I could do is I could actually model the absolute value and the sign as two separate models. And so I've got a binary classification model for the sign, and I have the absolute value. And then for my actual prediction, I multiply the predictions of the two models together. And so that's a way to go about this. Now, we don't like to be in the situation, and I just closed out a project for work where my predecessor had trouble getting the desired accuracy. And what they did was they actually had a model for positive and negative. They had a model for big or small, relative to given cutoffs, and then they had the actual absolute value. And in addition to that, they also partitioned by a covariance. And so there ended up being actually 7 different models. They didn't use big, small for one of those covariant levels, but there was a lot going on with that. There was a lot of things with it. And if you think about it, if I had 7 models, that's 7 opportunities for things to go wrong. Remember, every single feature that I have that's being used to make a prediction is an opportunity for failure because it might get data pollution. Maybe my organization stops collecting it. Maybe the database that holds that particular variable has failures of its own, technical errors. So every single predictor variable is an opportunity for failure, and then every single model on top of that is an opportunity for failure also. And so when we have a lot of moving parts, usually the model is not going to be able to endure for a very long time. We're going to have to refresh that model very quickly. We would prefer to have just one model for one target variable. That doesn't always work out. So that project at work, I was able to get that down to 2 different models. So how I approached that was that I used that covariate model to just say, 2 different populations, and then I just modeled the absolute value. And I worked with my stakeholders to say, hey, I don't need to worry about that positive negative aspect. And also, there were signs that the positive negative aspect wasn't even reliable for accuracy anyway. And so by using fewer models, for this one target variable, I was able to improve accuracy, and I have a more robust model that's probably going to last longer because it's much simpler. Now, how was I able to get better accuracy than my predecessor? Honestly, it was my data prep. Data prep is a huge aspect to your modeling. Specifically on that particular project, it was because I put more time and effort into the categorical data binning. I made sure I had good solid binning, went through, did a lot of analysis of that, and I had very good data prep on that. Therefore, I had better modeling, and the model is a success. It just launched into production, by the way. All right, so let's go ahead and talk about how we will approach it when I have when I make the decision, I'm going to have multiple models for one target variable. All right, so what we want to do, we want to break up our target variable into different aspects and then model each of those aspects. And remember, the more models we have, the more opportunities there are for failure when my model is in production. And so we can also anticipate that as time goes on, at least one of those models is going to start degrading as time goes on. So we also need to be refreshing. Models that have like multiple components like this are more likely to be needing refresh frequently. All right, so some things that we need to consider when we are working on this type of project, but when I'm going to take this approach. So we want to consider the complexity of our data. So if I've got pretty complex data, or I know I've got subpopulations, then this is actually a good choice for us to approach the problem. So if I've got different subgroups that have distinctly different behaviors. So in that project that I was just referring to, we had different payroll aspects that are going on, and we were divided out into two different clients. And so because of the difference in how the payroll relationship with the data, we need to split it out to get a better overall model. Now we can, so if I can get good solid accuracy without multiple models, I'm not going to use multiple models. But if I'm trying to improve things a significant amount, this is an option for us. And so when I have very, very diverse data and diverse behaviors in like pockets of data, then this multiple modeling approach is a good idea. So I can capture sub aspects. So when I have like large diverse data sets, one thing I can do is I can cluster my my predictor variables and use the clusters to identify subpopulations for the purpose of modeling and model on each of the different subgroups. All right, so there are some major disadvantages when we go through and we start using multiple models. First and foremost is our model overall is going to be a lot more complicated. So even if I had just like two logistic regression models, I've got two different sets of coefficients I have to interpret, I have to understand. If I've got something where, let's say I've got 10 subgroups, then it gets even more complicated. And I have to analyze each of these individually, and this can be a process. Also, it's going to take me longer just to build the models and to figure out what the individual model structures are. I have to identify each individual. I have to identify how I'm going to break up my data. I could break it up by target variable. I could break it up by predictor variables. I could split out the target variable by positive, negative. I could do subgroups of the target variable. There's a lot of different ways I could go about it. I have to go through and figure that out for this to work out. Typically in real life, when we're in this situation, just by trying other things, we've identified what those subgroups are, but maybe not. Maybe like we're just like, hey, what I'm doing isn't working. I'm just going to go for it. Now, we also have a risk of overfitting. Imagine the case where I had 10 submodels, building into my overall model. Well, that's 10 opportunities for overfitting. And so we always have to be mindful of this. And also, like, if I was to go through and do the clustering on the predictor variables, well, if I had too many clusters, then I'm going to be, getting smaller data sets, and potentially I could overfit on. I've got just more opportunities for things to go wrong. Also, it can be harder to validate and evaluate the model, because if I have all these different models, I have to go through and validate each one of them. I have to check their accuracy, evaluate their merits individually. And ultimately, I'm going to have a weakest link in this. If I had 5 models, well, I'm going to have a 5th, strongest model, which is my weakest model. And so, no matter what we do, we'll always have a weakest one, and hopefully we'll be able to get accurate enough, but probably not, because if accuracy wasn't an issue, I wouldn't be doing this. Interpreting the models can be super difficult because I've got all these different subgroups here and there. And, it might actually be easier for individual explanations, but now I'll have a lot more of them. So imagine I had, 10 subgroups that I built models on. then for each individual subgroup, I might have a stronger narrative to talk about, but now I've got 10 narratives to explain to my stakeholders. That's going to be a lot. Yeah, like my stakeholders probably won't even want to be interested in hearing me talk about it. Also, we're going to have to go through and combine them. And so, I've just got more code going on to put all this together. As a human being, I have more opportunities to make a mistake in my own personal code, the more code I write. And also, if I've got multiple models, I have to maintain multiple models to make sure that I've got a good solid output overall. Also, we can have conflicting decisions. And so the best example of this would be like a multinomial problem. So let's say that I have a 3-level target variable for classification, and potentially my models, my submodels, all say equal, equal probability for each of the 3. How do I handle that conflict? Also, if I'm getting into smaller sets of data, I can set it up so that I've gone too far. I've got smaller data sets than I really should be working with. And now I don't have the data to do the type of modeling that I want to do. So let's say I want to do, a neural network with so many hidden layers and hidden nodes. Well, if I keep on chopping up my data, it might be I don't have enough data to support that structure, even though for my project, let's say my stakeholders or my boss wants me to run with this particular model structure. And so, and when we start getting more nuance and stuff, we're going to need more expertise involved. We're going to need to talk about, what's going on with our stakeholders, see if this makes sense to them. Are they okay with it? And, you make sure we properly vet it with people who know what's going on. Sometimes as data scientists, we don't even have someone to talk to who is an expert in the field. We have someone who is new and learning things out just a little bit ahead of us as we work through the data. All right, so let's go ahead and look at some examples. So the first one I'm going to talk about is where I have a multinomial problem. So let's say that I've got 7 different levels of a target variable for classification, and there's a lot of different ways to handle this. But let's say that what I try with one single model for 7 levels isn't working out. It doesn't have the desired accuracy. Something I could try is that for each of the 7 levels, I could try to build a model where for level 1, I have a binary model where level 1 or not level 1. Then for level 2, I have another model for modeling level 2 or not level 2. Then for level 3, we have a model that's a binary model for level 3 or not level 3, and so on. And so if I have 7 levels for my target variable, I'll end up having 7 different models. And then after I have those models and I make my predictions, I'm going to use the predictions to make a decision on what should be the actual model or the actual predicted value. All right, so I'm going to go ahead and use Jacques Blackard's data set from Kaggle. Now, this is posted several places on the internet. This version is already cleaned up for use, so this is the one I use. There are other places that you can find this. I believe this is also on UC Irvine's website, but I don't think that's been cleaned up. Here it has dummy variables, and I ended up undoing some of the dummy variables to get binning, by the way. So the dummy variables were for wilderness area and soil type. All right, and so here I am, just loading my data. Now everything is in numeric format when it's originally loaded, and in this version of the data set, which is different from other places, is that the categorical target variable is coded as 1, 2, 3, 4, 5, 6, 7. And so I go ahead and I load it as a numeric initially, and then I go ahead and create it or convert it over to a factor. And I chose to put the factors in level of frequency for the purpose of interpretation. So it's not going to be in the order of 1, 2, 3, 4, 5, 6, 7. It's going to be in the order of the frequency in the data set for the levels when we take a look at it. And then we have soil type is a categorical data for this, and it's in dummy variable format in this asset. I went ahead and binned into two groups that look like they have similar distributions. I went through and used a chi-square test to compare different conditional distributions to see what ones look similar to each other. And I made the choice to put all of these into one group, all of the other soil types, which I believe they go up to 40, into a different group. Doing binary binning again, which I feel like is a good choice for initial runs, initial building of a model to see what covariates are important. Down, if I was doing this for a real project, I would get down the road, make other decisions, go back and double check that I see if I could do better on the binning. Now, wilderness area, there's 4 levels, and I'm putting 2 of them together. So I've got my binning is area 1 or 2 versus area 3 or 4 for this. And then I went through and took a look at the numeric predictor variables before the video, and I used Boxcox and Yo-Johnson to just see what's available. The only one that had Boxcox for the Keras package preprocess function was the elevation, and it was a power of 2. I looked at the histogram before and after, and squaring it does improve the distribution to make it look more like a normal distribution. And then for all of these all had Yo-Johnson transformations were selected by the Keras preprocess function. So I went ahead and built that here. And I'm going to be using logistic regression for a lot of these models. So I didn't center and scale because logistic regression, the accuracy does not improve off of location scale transformations. And so here I am transforming I'm using the predict function to transform all of these columns with the Yo-Johnson transformation. All right, so now let's go ahead and take a look at this one versus rest approach. So when I'm looking at level 1 for modeling, I have level 1 versus all other levels, the level 2 versus all other levels, level 3 versus all other levels. And I'm going to build 7 different models for this. All right, and I'm gonna go ahead and put them all into a list, make it all nice and neat, and clean this up. So I'm gonna go ahead and build a bunch of logistic regression models using the GLM function with family of binomial. And to make sure I don't have too many predictor variables that I don't overfit on my model, I'm going to go ahead and I'm going to pass all of my logistic regression models to forward selection. And I'm running this. The trace parameter says, don't give me output. Like, don't print it. And then go through and make predictions on each of these. And so I've got 7 different models, and each of those models individually makes a prediction of the probability of their particular level versus all of the others. Now, when I look at the actual results, and I'll show that in a moment, this will not be, I will have probability values on each row, but it will not necessarily be a probability vector. It probably won't be a probability vector. And so one thing I want to do in a little bit is rescale things to make each output of the 7 models together the like a vector of modeled probability of each different level. All right, so here I've got, so on this observation, we can see that we've got 0.94, 0.7. So right here, these 2 models, model 2 and model 1, together, if I look at their probabilities, I add them up, I can see that it exceeds 1. And then I've got these other values also, which are pretty darn small, but they're not helping, right? And so, especially 5. Now this column, this is the 2 models modeled probability of being level 2, modeled probability of being level 1, modeled probability of level 3, or we also say likelihood of 7, likelihood of 6, 5, and 4. All right, and so what I would do is for each individual observation, I would look and I would see, well, where do I have the largest value? Wherever I have the largest value, then I'm going to go with that one. All right, so I don't even need to rescale to make the classification, but to make things easier to interpret, I'm going to go ahead and do that. And so just looking at it, we can see that of the first 6, all but 1 have 0.9 or greater for the model probability of level 2. And so, that kind of just, now is that consistent? Well, remember, I ordered the levels by their frequency. And so we would anticipate to see larger, overall, on average, larger model probabilities for 2 than for 4. We would expect to see on average higher numbers on the left and lower numbers on the right as we go through. And here we can look at the bottom of the data set, so using the tail function. And so now we see some values that aren't as extreme. Let's see, so here it looks like here it's modeling 3 as being the level that it would go with. All right. All right, so let's go ahead and check the accuracy of our model. So in a multinomial problem, I'm doing a bunch of classifications. Our confusion matrix is our foundational way of approaching this. And so what I've done is I've got cover type here. So this is the true value, corresponds to the row. The model value corresponds to the column. Some people have that switched, rows and columns. Always just make sure you know what you're dealing with. Now, something that is good about what I did is you can, since I went through and put my levels in order of frequency in the data, it's a little bit easier to interpret. And so I'm expecting to see larger values at 2 than I see at 1 and 3 and so on. And now, so I'm nailing it when the diagonal values are large, and I'm flopping when the diagonal values are small. Okay, and then I'm nailing it when the off diagonal values are 0, and I'm flopping when the off diagonal values are large. So we can see here that I've got a problem that my model is saying it's level 1, but the true value is level 2. I've got an issue going there. So this is definitely something that I would want to address before I launch this model. Overall, I'm not really feeling a lot of love for this model, by the way. I would probably not put this into production. All right, so we can go through and we can get our confusion matrix statistics using the caret package. And we get our overall accuracy is less than a fourth. Wow, that's awful. That stinks. Here is a confidence interval for our accuracy, and and we can just go through and evaluate each of these. And you'll notice I've got a bunch of NAs for class 6. Well, why is that? Well, if I go back up to my confusion matrix, we can see that my model never predicted level 6. All right, so right out the gate, there's a problem with this model. Oh, and we know that level 6 has more observations than 5 or 4. So there's something going on. This needs to be addressed. And so part of the interpretation that makes this type of problem harder is that I need to go through and evaluate the sensitivity, specificity, positive predictive value, negative predictive value, prevalence, detection rate, all of these. I have to do these for each of the classes to make sure that things are good enough for my stakeholders, good enough for my project. All right, so let's say I was going to launch this model. Well, before I did that, I would want to know, like, what's typical for my predictions? What is the typical result? So how I like to approach that for this type of problem is to go through and do k-means clustering on the probabilities, and then do k-means clustering, and then use the centroids to represent like what's typical of that group. And so I'm going to go ahead and do that. All right, and here I am manually identifying what the centers are. And so what I wanted to do, I wanted to make sure I had a representation of when the probabilities are very large with an individual level. That's represented by the diagonal. Now here, this is when I have uniform distributed probabilities, and I'm hoping that like similar row vectors go there. And then this is what's typical of the overall data set as a whole. This is the average probabilities that I get just from the empirical data. And so here I've got 9 possibilities. Well, you run k-means with this, with the full data set, there's going to be some empty clusters. So I went through and eliminated it down so that a bunch of these were removed. And I put it in at least in my initial run, the order of which cluster had the most. And so here, this is where we can see that. So we can see that that overall average is going to have a good chunk. And uniform is a little bit behind, but not too far. And then predictably, the class that has the most empirical values in it has where the diagonal value, where the 1 and all zeros probability vector is coming in. All right, and so here we can see like the proportion of observations in each of these. So we can see that we have over 28% in that overall average one. We can see that we've got 28% in the one that's just really going strong with the first level, as how I have it ordered. And then we have things, so 4 comes up, so that is here. So that's the second most frequent level, major, and then the rest are relatively small. All right, so let's go ahead and visualize it. And so now I've got an idea of what is like typical for my probability vectors. And so we can see that in group 1, it looks like we have a conflict between the 2 groups, the level 1, level 2. We also see that level 2 is very strong in this probability collection. Then 2 is still strong, but we see that level 3 is popping up along with level 6. Here we've got levels 4, level 1, level 2, with level 1 being much stronger. A pretty tight competition between level 2 and level 3 on this. And once again, we're seeing level 1 pop up, and then we're seeing 3 and 6 come up like they did over here. So this is kind of interesting to see how it's going on. And if I was to go further, I would want to be digging into this. So it looks like most of the time, if level 7 is going to occur, it's going to be occurring in this 6th group. All right, well, let's see, what is that? So that I would want to analyze. So that's 1, 2, 3, 4, 5, 6. That is the 4th of the, that's interesting. The 4th of the 0, 1 row vectors. All right, so that's using multiple models for a classification problem. Let's start taking a look at how we could use multiple models for a regression model. All right, so a lot of times this is going to be like a binary model first, then regression models. And so what I could do a model where I predict the sign and I predict the absolute value, multiply them together. I could predict the sign, then depending on the sign, use one of 2 models, a positive value model or a negative value model, to combine to get together. Or I could potentially partition my target variable into different groups, do a classification of which group is going on, and then on each of those groups have a regression model. There are a lot of different ways we can do this. And further, you go even further with this, we could group our predictor variables, such as with clustering or some other method, maybe with a covariate that we know is very important, and on each of those subgroups of my predictor variables, build a model for the target variable on the regression. So then when I make a prediction, I have to classify which group, which is a classification problem, and then depending on which the classification comes up from that model, I select a particular model for the regression value. And so, there's a bunch of ways to approach this. All right, so here I'm going to model the sign of the target variable. Then I'm going to model the absolute value. For predictions, I just multiply them together. And so to make this a little bit more interesting, I created a positive negative variable for us. So I did Boxcock's sales price minus its median. So then, approximately half are positive, approximately half are negative. And so I built a logistic regression model to model, is this positive or is this negative? And then when I would put this into production, so here is how I'm modeling if it's positive or negative. When I'm in production and I make a decision on, oh, this is positive or this is negative, then what I'm going to do, I'm going to model the absolute value using just linear regression to make it simple. I'll use linear regression to model the absolute value, and I'll multiply the predictions together. And that's how I'll get my actual predicted value. And so here we can take a look at our train test and validation statistics. All right, so now let's talk about partitioning the target variable, and then I'm going to have a regression model for each of the partitions. So I could put this into two different groups, maybe like big and small. I could do this into positive or negative, or I could do like clustering or some other like known subject matter knowledge aspect to figure it out that way. And so my first goal when my model is in production is to predict which group the target variable will be in, and then I'm going to go through and pick the particular model that's going to run. This is different from what we did a moment ago, because what we did a moment ago was on absolute value. I used the same model every single time, regardless of if I had positive or negative classification. Here, I have a different model for each classification level. So there is a difference, and you'll notice it's a more complicated process. So I need to model like which partition my target variable will be in. And then after I get that, I'm going to select a linear regression model that's appropriate to, figure out what's going to get my predicted value. And so here you'll notice I just went with two linear models to keep it less complicated, but potentially I could have more than that. And so, I'm going to have different models going on. Check out that, I've got different coefficients. Both of these I put into forward selection to make sure I don't overfit. And so when I go through and I actually make my predictions, I'm going to only use one particular model. And so in this code, I actually run, for every single observation, I run both regression models, and then I select which model am I actually going to use using an if-else statement. Not the most efficient way to do this. If I had millions and millions and millions of rows of data, this would not be the fastest way to do it, but the code is simpler, so I chose to do it this way. And so now we can get our train, test, and validation statistics, take a look at what's going on. Now, I want to talk about partitioning on the predictor variables. So now here, this is different than what I had a moment ago. Previously, I used a supervised learning model to classify what level my target variable is going to be in. So I'm predicting in a range what my target variable's value is going to be. Here, I'm working on my predictor variable. So I know exactly what group it's in. I know there's no ambiguity, nothing to guess, there's no accuracy aspect to this. So what I'm going to do is after I get my data, I'm going to group my my rows of data in some way, shape, or form based off of the predictor variables. In this example, I'm going to be using k-means clustering, but it could be based off of one single covariate that my stakeholders believe is very important. And then each subgroup of my records is going to have a different model. And so when I get into production, first thing I'm going to do is identify which group a record goes into, and then I'm going to grab the particular model for that group, make my prediction. So here I am running k-means. And so here I'm creating the partition vector off of this by using the prediction function on this version of k-means. This is not the stats package version of k-means. Here I am using this package version of k-means because it has a better implementation of the predict for new unseen data. All right, and I'm just going with 2 groups just to keep it simple and easy on myself. And so, here we've got this. Now, something I should have done, I should have rescaled my data beforehand, but it's always important to rescale your data to have, approximately constant variance, column variance before clustering. And so then for each one of those clusters, I'm going to go in, I'm going to build a regression model. Here I'm using linear regression and to build it. And I'm going to go ahead and do forward selection to protect myself from overfitting. And so here are my 2 models. And we can see that they are in fact different models. If I look at the coefficients, these are different values, and these may or may not have different predictor variables. They may be the same. And so when I actually launch my model into production, I'm going to have to make a decision on which model is going to be used for each one. So I get my record, I identify which group it belongs to, then I grab the corresponding function, make a prediction, boom, I've got the predicted value. Here, how I chose to do it is I went through and I used all the, both models to make a prediction, and then I used an if-else statement to identify which one to keep. Not the most efficient code, but for this purpose, it's relatively simple. And once again, I'm going to go through and check out my test, train, and validation statistics to check to make sure I have a good model. And remember, on each individual group, I have to evaluate this. I have to evaluate each individual model that I have to check to make sure that I've got something worthy of putting into production. All right, so for your homework, go and take your data, build a hybrid model, and that's it. All right, how you do that, it's up to you. For the classification, you could do for the different levels, you could do negative, positive with absolute value. However you want to approach it, whatever is most interesting to you, whatever works for your data is what you should be going for. I'm not going to dictate how to do this hybrid modeling. All right, well, that's all I've got for you. Life is short. Do math.